Thanks for joining me for some homework help on two-body problems that we started in class during lab. What I'd like to do is just as a refresher, what we talked about in class was the fact that you could use a system, something like the one shown here, as kind of an analogy for working more complicated problems. And in this case right here, what we said was that to figure out information, for instance, like the acceleration of the blocks or the tension between the two blocks that are moved in this way, it could be helpful to treat the system as a single unit, so as one object. And when we do that, we get this benefit, is we can write a very simple force equation. In other words, the sum of the forces now becomes the sum of the forces on the system, and the sum of the forces on the system becomes equal to, well, in this case right here, a frictionless surface, so I don't have any forces associated with that. The only force on the system is the hand, so we'll call it the force of the hand simply. That'll be equal to the mass of the system. So in this case, that would be the mass of A plus the mass of B, the total system. And that would give us the acceleration for the entire system. And of course, since A and B move together, that's also the acceleration of A and B, and that's what makes this approach kind of nice. We can solve that thing by simplifying. Now, if we're asked the question, for instance, about what the tension in the rope is, using the system as a whole won't help us because the tension is an internal force. And when you do motion problems, you're not concerned with forces between things that are inside the system. So what we have to do is we have to go back out and we have to break the system up again now into two different parts. And we're going to write another force equation. In other words, the sum of the forces now acting on just on block B. And in this case, that's fairly straightforward. That is just the tension force, no friction. If there was friction, of course, we would have like a minus F or something like that. In other words, we could put in other forces that were acting in the horizontal direction. In this case, just the tension is equal to the mass, but now it's just the mass of block B times the acceleration. And conveniently, we have found that information from this equation down below. And so you can kind of see here, we can go back and forth between finding the acceleration of the whole thing and then the tension or forces within the system by using this technique. Then the next thing we said in class was this, that the situation that you see in this case right here is very similar to the previous case. In other words, what happens in this case as shown is you have object A, which is 0.2 kilograms or has 2 newtons of weight acting in this direction. The object C here has 4 newtons of weight acting in this direction. And it's pretty clear when this thing is released, it's going to have some kind of a motion that's in this direction. Now it's not really clear because it's not left motion or right motion, but you get the idea that the system is still moving as one object. In other words, A and C both have exactly the same acceleration and they have the same tension in the string. And so that allows us, by analogy, to use the same type of approach that we used for the previous problem. And the way that works is this, is to answer, let's say, the question about the acceleration of the blocks. What we say is we treat this all as a single system. Now this looks kind of goofy, but it'll help us out here. It's a weird system. It's a system that is kind of going around a corner, but that doesn't matter because we can still write a force equation associated with the system as a whole. And that force equation would be, in this case, unbalanced. And since we have 4 pulling down on one side, 2 pulling down on the other side, we can say it's balanced or unbalanced 2 newtons, kind of in the direction of the gray arrow here, in that direction. So, and that's the only net, that would be the net force acting on our system. That's going to equal the mass, but that's the mass of the system as a whole, in this case 0.6 kilograms, times the acceleration. And you can see that this approach allows us to fairly simply solve for the acceleration of the blocks. This will help you on one of the final problems on the lab sheet. Now, we can also answer the question about the tension, and in this case right here, the tension is not the weight of A, and it's not the weight of C. It's going to be somewhere in between. And for calculating that number exactly, what we need to do is follow that same procedure that we used before of isolating just a part of the system. That way we can get our tension force. And if I write a Newton's law equation for just object A, I would get something like this. Tension is pointing up. Weight is 2 pointing down. That's equal to the mass, but it's the mass of only block A, so that's 0.2 kilograms, times the acceleration. And conveniently, we have solved from above this acceleration, so we know this number, and you can see that this would be a method for finding a value for the tension. And that's the general approach for working with these they call them two-body problems. Now there's another way. We could have also chosen block C. And I'm going to do this because it presents itself something that you have to be a little bit careful of. Let's go ahead and do the free body diagram for block C. Let's say I wanted to find the tension by using C. I'd do sum of the forces on object C. In this case, it would be T, which points up, minus 4, which is the weight of the block. No other forces acting on C, so it would be the mass of C, 0.4, times the acceleration. Now, in this case right here, this is where I wanted to give you a caution. Throughout the entire procedure of this, using the system as an analogy of the horizontal problems, we've kind of been a little bit squishy about directions. We haven't really defined directions like we have for other vector problems. But this is where you have to be careful. Object C, the acceleration for object C is acting down. The acceleration is in this direction. And what that means is if we had chosen block C to find our tension, we would not get a correct answer with a positive value for acceleration. We would have to make it match our free body diagram. In other words, we would have to account for the direction of the acceleration when we went to go make that calculation right there. Okay. Now this is a little bit self-correcting if you realize what's going on, because if you did not have that negative sign there, in other words, if you weren't multiplying by negative A, which I just want to make sure you realize I'm not subtracting here, I'm multiplying by the negative of A. If I didn't do that, I would actually end up with the tension greater than the weight on C, which would no longer match the direction of acceleration, and it's maybe self-correcting, realizing that what we had to do was account for the direction of the acceleration when we made that calculation. All right, so what that's going to do is that is going to help you, hopefully, with these last questions. These mathematical questions about the direction of acceleration and the value for tension on the block. I want to take a moment to get you started on the remaining portion of your homework, and that gives you an opportunity to practice this. You can see it. This idea that we've talked about works in different orientations. So here's an example where you have a block that's sliding across a frictionless table, and only one of the blocks now is suspended. But you should be able to know, and I'm not going to go into the actual solution, but you could realize here, if you're asked about the acceleration, of course, we can treat this whole thing as one system. It works similar. And then if we're asked a question in the course of the homework about a tension, for example, you could treat it after you have the acceleration, you could go ahead and treat it as one of its parts. And that little procedure should help you with both of these problems. Here's one orientation. And here's one that's just a little bit more complicated, but you should be able to handle the fact that you have a weight component down the plane and do the same sort of a setup. Now, finally, I have given you solutions for these two problems, so you can check your answers. I have not given you solutions for this one, however. These 2 pages here are your homework due on Tuesday night at midnight. And this one I won't give you a solution for. This is what I'll grade. But with everything we've talked about, you should be able to handle this AP problem. You can kind of see this AP problem was actually one of the problems on the test just last year. So, so it's quite current. You can kind of see here a question about the acceleration of the blocks in this format, and then a question about the tension, and then a motion equation about the actual what's happening with the motion. Hopefully this helps you get through the homework assignment and learn a little bit about these more complicated motion problems with 2 objects. Thanks for joining me.